In this video, we'll start a discussion of Factorial ANOVA, which is an extension of both the one-way ANOVA and the randomized complete block design. So this in the textbook is going to be chapter 5. We're going to go over some of the general principles that are involved with these factorial experiments. We're specifically going to focus on two-factor experiments. In this set of videos. We'll reference more, but that's going to be the primary focus. We're going to talk about doing ANOVA for factorials and go in depth on how we do that. Talk about how we can again extend into the broader case, and then quickly talk about a few other things, including qualitative and quantitative factors. So the very first question is, what is factorial ANOVA? And when should you use it, and why should you use it, and when should you not use it, all that stuff. So we've had the one-way ANOVA, which involved doing an ANOVA with a single independent variable. When we talk about factorial ANOVA, another way to think about this is a multi-way ANOVA. Just like a one-way ANOVA had a single independent variable, in this case, we're going to have multiple independent variables. Now, instead of just controlling for another variable like we did in the randomized complete block design, in this case, we actually want to test the other variable at the same time. So we're not just having a single control variable. Again, randomized complete block design, we looked at a control variable that we were accounting for. But in this case, we're actually interested in both of the different factors. Again, we're going to have two or more categorical independent variables. So these are two independent variables, but remember, with all of the independent variables in the ANOVA framework, they need to be categorical. That includes blocking factors too. And then we have one continuous dependent variable. This is the exact same thing as we had. Now, when we have different specific numbers of factors, so like two independent factors, two independent variables, we call this a two-way ANOVA. If we had three independent variables, we'd call it a three-way ANOVA. That's about as high as we go. After that, we just tend to call it a multi-way ANOVA or factorial ANOVA. But all of these fall under the broad framework of factorial ANOVA. In this, again, series of videos, we're going to focus on two factors. So primarily, we're going to be looking at two-way ANOVA. But you can think of when we say blank way, one-way ANOVA, one independent variable, or one factor, two-way ANOVA, two independent variables, three-way ANOVA, three independent variables, etc. Now, we should contrast this with the randomized complete block design. We'll talk about this in a second. But factorial ANOVA often includes an interaction term. And we're going to define what this interaction term is in a bit. But this interaction term is huge. So I definitely put a little star next to this one. Because this is a big piece of what makes a factorial ANOVA really, really interesting, above and beyond what we've already done with the one-way ANOVAs and the randomized complete block design. Now, the theory, though, is very similar to what we've worked on previously in both, again, one-way ANOVA and randomized complete block design. Okay, so distinction from the randomized complete block design, there are three main ways that we can distinguish the factorial ANOVA from the randomized complete block design. Excuse me. First is the research question. So in the research questions, this is where we're asking about the variables that we're interested in. What do we think affects what? So in the randomized complete block design, we would just have the independent variable in the research question. We might say something like controlling for blank. Actually, even there, it's hit or miss. In the factorial ANOVA, though, our independent variables are going to be in the research questions. Said another way, that's just saying these are variables we care about. These are variables that are important to our research. Blocking factors are just things we controlled for. They were kind of a nuisance that got in the way of us studying our research question. But in a factorial ANOVA, all of the variables are going to be part of our research question because they're variables we actually care about. The second thing that we're going to look at is randomization, and this is the second distinguishing factor here. Remember, in randomized complete block design, the block expressed a limitation on randomization. So when we were doing our random assignment, we couldn't randomly assign across blocks because, hey, the block reflected a restriction on that randomization. That was a big piece about what made a blocking factor a blocking factor. So now we're not going to have that restriction. When we have our second independent variable or third or fourth or whatever, again, I'm going to tend to go with 2 for the examples in this slide deck. So this randomization is going to be an unrestricted randomization. We should have full control. This is called a completely randomized design, where we randomize across the entire experiment without having any of those limitations that we discussed in the last chapter. Last but not least is this interaction term. So in the randomized complete block design, we did not include an interaction term. And we hadn't really discussed what an interaction term is. I'll be honest, I was a bit debating, should we present this where we talk about interaction terms first, randomized complete block design, which kind of comes ahead of this in terms of theory. Ended up doing randomized complete block design first. So we haven't really discussed this interaction term. We're going to go into it in a second. But this interaction term wasn't present in the randomized complete block design. In fact, in some ways it can't be present in the randomized complete block design because we're using a blocking factor that we don't care about. So the interaction term becomes a factor we don't care about, and the randomization restriction means that we can't study the blocking factor or the interaction term in a way that we do care about or that is statistically valid. So now that we're in a completely randomized design, this factorial ANOVA, this interaction term gets included. And in fact, in factorial ANOVA, as we said in the previous slide, the interaction term is very often going to be included. It's going to be the default to include this interaction term, and we should have a good reason not to. Now, what's kind of interesting here, we might make the interaction term, now that we're on this topic, this might be our main focus of a study. I have definitely done studies where the whole purpose of the study was the interaction term itself. And that's, you can absolutely do that. That's absolutely a thing. So if you do this, you may or may not actually care about the individual or the independent variable that you added. In fact, in some cases, you might not care about. I've used independent variables that I don't care about so that I can look at the interaction term. Now, if I include an independent variable that I don't care about so that I can look at the interaction term, I don't want to include it as a block, even though I don't care about that main independent variable. If I care about the interaction term, I want to make sure I'm using this factorial ANOVA framework with the completely randomized design so that I can look at the interaction term itself. All right, so let's talk about the model. We're going to be using fixed effects. There are random effects, factorial ANOVAs. They're actually really cool. There's mixed effects where we have both fixed and random for each of the different independent variables in there. I highly encourage you to check out the textbook. I think one of the chapters at the very end of the textbook deals with the rather complex situation of mixed effects variables and how that plays out. You can also do all of them being random effects, in which case it's not super different from what we're going to see today. The treatment effects for the two-way ANOVA, so again, we're going to be focused on the two-way ANOVA here. We've got our grand mean, we've got alpha. This will be the different means of factor 1 as adjusted by the grand mean. Got beta, the different means of factor 2. Remember that alpha is the addition, so we start at the grand mean, and then we go up or down for each of the levels of factor 1 by these values of alpha. So this is the adjustment from the overall mean for each of the levels of the factor 1, and beta is that same adjustment for each of the levels of factor 2. So we've got subscripts I, j, and k. I is going to be the number of levels in factor alpha. J is going to be the number of levels in factor beta. Again, the textbook uses A and B. I'm going to use, well, it depends. I've followed the textbook here, but I tend to use capital I and capital J just to reflect I and J. And then K is the number of replications within each cell combination. Now, the cell combination, let's say alpha, I don't know, gosh, let's say male, female, and beta is you are a surfer versus a swimmer. Then little n is the number of combinations. So like male surfers, male swimmers, female surfers, female swimmers. Each of those four would be a combination. Little n would be the number of replications within each one of those, not within an individual factor level itself. So it's not the number of males, it's not the number of females or the number of surfers, it's the number of individuals within that combination. So the text uses tau in place of alpha. Alpha and beta make more sense to me, but Just so you know, alpha and beta are called main effects. So one of the terms that I didn't explain in here is this alpha beta ij. So this alpha beta ij, this is that magical interaction term that we're going to be focusing on a lot of today. So alpha and beta are called the main effects. This main alpha, this main beta left alone. So these are the main effects of our model. This is like the effect of sex, and this is the effect of your chosen physical activity. The alpha beta term is called the two-way interaction. Two-way because we've got two variables. You can have 3, 4, 5-way interactions. This is the two-way interaction, just like a two-way ANOVA, between alpha and beta. So that's what this term is in our model. This is our interaction term expressing the two-way interaction between alpha and beta. So let's go on and dive into this. What is the interaction? So an interaction can only be there when we're looking at three variables. So we have to be looking at least three variables. In the case of the previous model, we're looking at 2 independent variables and 1 dependent variable. That makes 3 total variables. So that's a case when an interaction could be present. When you look at 3 variables, that doesn't mean there necessarily is an interaction. But all an interaction is expressing the idea that the whole is different than the sum of the parts. It's not more, it's not less. We don't know. It could be either one. But if it's different, then that would be the presence of an interaction term. So let's do a quick dumb but obvious example. Let's say that we're doing a food rating score. And so I have a food rating score for steak, and you give steak a 10 out of 10 because steak is amazing. And I have a food rating score for key lime pie, made with fresh key limes, of course. And you give that a 10 out of 10 because key lime pie with fresh key limes is amazing. But then if I put those together and stuck them in a blender, the whole score out of 20 isn't going to be the 10 from the steak plus the 10 of key lime pie. A steak and key lime pie blended together milkshake isn't going to be 20 out of 20, right? The whole is different than just adding together each of the different parts. So that's the idea of an interaction effect. So if the effect of alpha is strong and the effect of beta is strong, but then I put them together, they could be not as strong. Or maybe when I put them together, they could be even stronger. So that would be the presence of an interaction effect if that tended to happen. Said a different way, what ends up happening is that one independent variable affects the relationship between the other independent variable and the dependent variable. We'll have an example later on. But in this particular case, what you have is that the relationship, let's say the relationship between beta, the second factor, independent variable, and the dependent variable was very positive. But let's say that when we look at different levels of alpha, beta only helps on the dependent variable if you have alpha. So actually, here's a really great example. My super cool teaching method. Dr. Florin has this amazing teaching method, and hey, he's got this really cool laser pointer that he just learned about. And how effective is this really cool laser pointer on the PowerPoint that he just learned about? Well, the laser pointer might be the most effective thing in the whole wide world, right? So the relationship between using a laser pointer, my independent variable, and student learning, my dependent variable, might be really strong. But let's say my students didn't come to class. So this coming to class variable, this other factor, might affect the relationship between my use of the laser pointer and student learning. So let's say my use of the laser pointer was really good for student learning, but if students don't come to class, my use of the laser pointer is no longer really good for student learning. In fact, my use of the laser pointer doesn't affect student learning at all because a student didn't show up for the class to even get that effect. So that would be a case where students showing up to class, one independent variable, might affect the relationship between another independent variable using a laser pointer and the outcome, student learning. Note that we can't really determine a direction here. So this goes into the different natures of the ways in which these variables could be related. And I say can't. We're in experimental design so that there are sometimes ways that we can do this, but by default we tend to assume that we can't tease these out. So let's say that my use of the laser pointer was actually what affected students not coming to class or something like that. Said another way, maybe it's easier to look at in theory. This kind of looks like alpha times beta. In fact, it is alpha times beta in a regression standpoint. We're not going to go into the details here, but multiplication can be switched around and it's still the same. This is the same as beta alpha. We don't know if it's alpha affecting beta's relationship with y or beta affecting alpha's relationship with y. It could be either one unless we have a theory reason to support otherwise. And again, I mentioned this, it almost in this equation looks like these are being multiplied together. When you think about interaction, it doesn't really work when both of these are factors like in ANOVA, but let's say this was regression where both of these are continuous values. This literally would be multiplying these continuous values together. So this interaction term really is kind of like multiplying these. Again, it's a little different in ANOVA because these are factors, but that is the idea and that is the intuition. All right, so we've just been looking at the equation, but let's dive in and look at the main effects and interaction effects graphically. So in this case, these are similar figures to what you've seen before in class. We've got factor A at a low level and a high level, and factor B at a low level and a high level, the minus meaning low, the plus meaning high. And we've got the different levels of factor B for each of the different levels of factor A. So if I look at this, B plus is clearly higher than B minus. So if I took the average of B plus, or the average of the effect of B, plus minus the minus 1, I get this number 11. If I took the average of factor A, well, factor A for both levels of B, when factor A is positive, that's higher than factor A being negative. So my little dot up here would be kind of the average effect of factor A plus. My little dot down here would be the average effect of factor A minus, so clearly A plus is higher than A minus graphically, and when we do the calculation we see, yes, actually it is. And then down here, this is the calculation of the interaction effect, and I think we've shown this on previous slides too. It's where we're looking kind of on the diagonals. All right, so this is a case where there is no interaction effect, or very, very, very small interaction effect in comparison to the size of the main effects of the two independent variables. So the main effect of A is that the plus side is higher than the minus side. The main effect of B is that being B plus is higher than being B minus. And note that that doesn't mean that B plus is at factor level A minus is higher than B minus at factor level A plus. That's just saying within B, plus is going to be better than minus. And within A, plus is going to be better than minus. All right. So jumping ahead, here's the case where we have an interaction term. And actually, a disordinal interaction is one where the lines physically cross each other in this picture. They don't always have to cross within the picture, but it's a good indication, especially in this design where we have just two levels of factor A and two levels of factor B. Then we look for that crossing pattern. In this particular case, let's try to tease out, like before we said it was better to be a plus factor A than a minus factor A. But looking here, here's about my factor A plus mean. Here's about my factor A minus mean. And it's kind of tough to tell if you're going up or down based on being factor A plus. And in fact, you see the effect of factor A is just 1. It's kind of tough to tell. Same thing with the B plus and the B minus. So B plus, the average of B plus is maybe about here. The average of B minus is maybe about here. So it looks like B minus might be a little bit better than B plus. The effect of B might be negative, but it's still really close. And here you see, yeah, -9 is still pretty close. This interaction term, though, last time it was about 1 or -1. Now it's jumped up to -29. It's way bigger than both of our main effects. And this is a great example of what an interaction plot does. Now, I want you to think about what you would get away from this graphic, or what you would take away from this graphic, and we'll come back to that in just a moment here. All right, so our practical interpretations of the interaction. All right, so in the interaction term, the interaction affects the interpretation of the main effects, affect, effect. So the interaction term messes up how we interpret main effects. Let's go back into this. Here in factor A, I can clearly say being a positive on factor A is better than being a negative on factor A. But in this plot, that doesn't really work. That's not necessarily clear as being a plus on factor A good or a bad thing. In the case of if we were a B minus, so this is the line for B minus, for B minus people, getting a plus on factor A is a really, really good thing. If I was let's say that this means I was a swimmer, and remember female and male. So if I was a swimmer and this is how happy I am with life, then it would be better to be a male than a female for being a swimmer. Factor A plus would be better than factor A minus if I'm at level minus on the B factor. But if I'm at level plus on the B factor, let's say I'm a surfer, level plus on a B factor, then I'd be happier if I were a female than if I were a male, for whatever reason. So this is a great, actually, illustration of how this messes up the interpretation. It's not just you're happier to be a surfer versus a swimmer. It's not just you're happier to be a male versus a female. It's really focused on well, it kind of depends. The interpretation of which is better, surfing or swimming, depends on if you're male or female. The interpretation of which is better, male or female, depends on if you're a surfer or a swimmer. So these interpretations depend on the levels of the other factor. And going back to what we were talking about earlier, this is where we're talking about the independent variable affecting the relationship between the other one and the dependent. And we know this. A good thing to jot down in your notes is to say it depends. So if the interpretation of an independent variable and the dependent variable depends on what level the other independent variable is, then you can say that that other independent variable is affecting that relationship. Contrast that with this. Let's say, what is it better to be B minus or B plus? Well, it doesn't matter if you're factor A minus or factor A plus. In both cases, it's better to be a B plus than a B minus. And vice versa. Is it better to be an A plus or an A minus? It doesn't matter if you're a B minus or a B plus. For both cases, it's better to be a factor A plus than to be a factor A minus. But in this case, with an interaction, the interpretations aren't so clear cut. In fact, interpreting that it's better to be an A plus in this case is true for the B minus group, but it's not true for the B plus group. So interpreting the main effects of a factor when there's a statistically significant interaction can actually be extremely deceptive, and we really need to look at these plots to interpret that. So this can absolutely affect the interpretation of the main effects, and because of this, this affects our procedures. So what ends up happening is that the procedures become, we still first look at our assumptions. We still check our assumptions first, but then right after the assumptions, after all our assumptions pass or we fixed them or whatever we have to do, obviously if our assumptions don't pass, we don't continue. But after we fixed our assumptions and they pass, we then look at interaction before we look at anything else. If there is an interaction, we say that we have to stop and we can't look at main effects. We have to go and look at one of these plots to figure out what's going on behind the scenes here. The main effects of our statistics are going to be deceptive in the case of an interaction. This plot is called an interaction plot. So in the case of a statistically significant interaction, we stop interpretation and we go look at the interaction plot. In the case of an insignificant interaction term, then we go ahead and we interpret as normal. So it looks like A plus is better than A minus, it looks like B plus is better than B minus, and we go on and we interpret that just like we normally would. So this is our new procedures. Again, if there is an interaction, we stop, we look at the interaction plot, we do not interpret the statistical significance test of main effects. If there's not an interaction, then we can go on and we can look at the main effects, that is the effect of alpha and beta, just left alone. So this is a very, very important thing. Make sure you're writing this down. Go back, rewind, Write it down because this is very, very important, as this really affects the procedures and the way that we look at it. Assumptions are the same before, except that if we don't include the interaction term, we're not forced to include interaction, but if we don't include the interaction term, we're making an assumption that there is no interaction. So in the case of an interaction, to assume that there's not an interaction is really going to throw things in the loop. So including an interaction term is going to be just fine. Our assumptions are the same as before, but if we choose not to include it, we're adding an additional assumption that the interaction is 0. And again, that can affect model fit, just like if we include a wrong variable or fail to include a useful variable. If we fail to include an interaction term that actually really needs to be in there, that's going to impact model fit. In the next video, we'll keep going and we'll jump into a few examples of how we do some problems with interactions, talking about some of the different calculations that we do, how we complete the ANOVA table, and again, practicing our interpretation.